Today I'm going to talk about another sampling-based path planning algorithm called the RRT-Smart algorithm, which is an enhancement on the usual RRT-star algorithm. This is presented by me, Ashraf Faraj, January 21st, 2024. Now, as usual, the goal of the project is to plan a collision-free path from the start node to the goal node shown here. So the following figure here shows an example of a path generated by the RRT-Smart algorithm. The figure is taken directly from the main paper that actually suggested this algorithm for the first time, and I'm going to append the link to this paper in the description box. So we can see here that the straight edge characteristics of the RRT star tree is still there, but we do notice here that there is a higher density of nodes here at the points of the vertices of the obstacles. So this is what actually one of the main ideas that the RRT star smart algorithm uses. It focuses on the idea that the nodes on the path leading to the goal actually contain information regarding the vertices of the obstacles or the boundary of the obstacle. So it would be beneficial to sample around these points in order to enhance the quality of the path as much as possible. Now that's the main idea of the RRT Smart algorithm. Now we're going to explain the RRT star Smart algorithm in detail. So first, we initialize the nodes and the edges. Then we initialize the tree and the cost array. Now we repeat the following steps for a maximum number of iterations n max. Now the first change that the RRT star Smart algorithm does is uses intelligent sampling instead of the ordinary uniform sampling on the free space. Now this is done using a function called intelligent sample, which we're going to discuss in the next slide, which takes a Boolean goal found, indicating whether the algorithm has found the goal or not, the goal index, I, which is the index of the iteration, and beacons, which is a set of nodes on which the intelligent sampling is to be based. We're going also to discuss how to compute those in a minute. Then we compute X neighbors, just like in the normal RRT star within a radius R. The choose parent is also similar to the RRT star, and rewiring as well. Now, if the newest node that we just found is in the goal region, then we save the goal index and we indicate that we have found the goal by setting goal found equal to true. Finally, we use the function optimize that takes a path, the current path, from the start to the goal and tries to optimize it by pruning some of the nodes on this path using a method that we're going to discuss just later on. Now all of this is just repeated for a maximum number of iterations n max, and then we return the path to the goal if found. So now we're going to discuss the intelligent sampling, which takes a Boolean goal found, the goal index, I, the index of the iteration, and beacons, a set of nodes on which we will going to base our sampling. So the figure here will help us understand how the intelligent sampling works and what's the purpose of it. So right here we have all the nodes right here. The small circles are all nodes in the tree. The black edges are the edges connecting the nodes. And the green nodes are the ones that are on the path between the start and the goal. Those are what we call actually beacons. So now the golden circles are the radiuses in which we are going to sample from. Okay, these circles are around the beacons, okay, with a radius of r. So when are we going to sample from these beacons? That is, if we found the goal and if the index of the iteration is actually goal index plus b multiplied by a natural number, which means that we're going to actually perform this type of sampling from these beacons if and only if we found the goal, and only once every b iterations. So if b is like 3, then we're going to wait until we find the goal, and then we're going to sample every 3 iterations from these beacons. Now, why is sampling from the beacons actually beneficial? That's because we believe that the beacons contain information regarding the boundary of the obstacle, as can be seen here. Now, else, we're going to use just the normal uniform sample from the free space. We're going to discuss the second important function that is associated with the RRT-Smart algorithm, which is the optimized path function. Now, this function would take a path from the start node to the goal node and tries to optimize it by pruning some of its nodes. Now, the figure here to the right would help to illustrate the idea of the optimized path. So here the green nodes are all nodes located on the path from the start to the goal, and the red rectangle is an obstacle. The black edges are edges of the tree, and we call the nodes node X, Y, Z, W respectively. So the main idea of the optimized path algorithm is that, for example, if we are now checking for node X, we're going to check if we have a collision-free path from node X to its grandparent. So in this case, the parent of its parent. So that's going to be node Z. We're going to check if there is a collision-free path from the current node to its grandparent. And if there is, we're going to actually connect it there and remove the connection with the previous parent. We can see, for example, that in the case of node X, that is not possible because of the red obstacle located here. But for node Y, we can see that the grandparent, which is node W, can actually be reached by a collision-free path, as can be seen here. Now, this would actually help to show why this is actually would reduce the cost. That's because our cost function, which is the Euclidean distance, satisfies the triangle inequality, meaning that this length from node Y directly to node W would be smaller or equal to than the sum of distances from node W to node Z, and then from node Z to node Y. Now, how to implement that? We're going to actually implement this by, first of all, using a while loop. While there's actually no more changes to the path, X is equal to the goal index, we're going to start at the goal index. Now, while X has a grandparent, if there is a path from X to its grandparent, which is obstacle-free, we remove the previous edge between X and its parent, we add the new edge between X and its grandparent, then we update the parent of X, we update the cost of X accordingly. Finally, we must update the cost of all the children of X, which are down the path towards the goal, because their cost will also change once we change the cost of this path. Then we're going to set X to the parent of X just to move on to the next node. Results. Here on the right, we can see a figure showing the path found by the RRT-Smart algorithm on the kilobot example. We can see here that the tree was actually successful in finding an optimal or a near optimal path, as can be seen here in blue, which is actually not that far-fetched, because as we said, the RRT-Smart algorithm is actually based on the RRT-star algorithm. So it's actually asymptotically optimal, meaning it's guaranteed to find an optimal path if the number of nodes tends to infinity. Now, as a conclusion, in this project, we discussed the RRT-Smart algorithm in detail. We discussed the two main steps, mainly the intelligent sampling and the path optimization. Then we implemented and tested the RRT-Smart algorithm on the kilobot path planning problem, and we found that it actually achieved an optimal or near optimal path quality. And that's it for this project. Thank you very much for listening.